Okay, I've been reading this book that is Introduction to Chaotic Dynamical Systems by Devaney, and I guess this cover is just a fractal, and I'm gone through the hyperbolicity section, so I'm just gonna review that right now. So, so originally I didn't know exactly what this type of 2D graph meant, but I kind of understand it now. And basically, what it says is that if you have some point that is like this, that is clearly periodic with period 2, then if you take this point with this x value and then map it up to where the f of x is, and you kind of keep doing iterations on that, and uh, yeah, so basically, this graph, which is a phase portrait, is a little bit kind of confusing because you kind of see why are the boxes going around and why is the line y equals x. But this is basically essentially trying to explain or show geometrically how the function takes points and then what it sends it to, and what would happen if a point just kept being iterated by the function. And usually it's less precise than calculating the function value, but it allows you to see exactly how fixed points behave, like what geometric shape they pick, and this also kind of looks like a fractal. So what is this phase portrait basically trying to say? It's basically saying that if you take a point in some x value and you want to keep reiterating what happens as you apply f to it, which is the mapping or the discrete map, and basically this is trying to geometrically show where each x value goes as you keep adding the function, applying the function to it. And I don't think this is a very good example of what it looks like. I mean, this shows the picture, but you don't really understand why there's boxes moving around, why the lines straight going through x and the identity map and also the function, which is negative 1/2 x cubed plus x. So I'm going to draw it again. Okay, so basically this is the R2 and this is an identity map. Actually, the identity map doesn't make sense why you draw it now, but later you'll see that it's kind of important for how you reiterate the function. And so basically, let's say I wanted to find this x value, I would go to this x value, and this, when you apply f once, this is what it does, right? It sends this x value, like x equals something, to f of x. So this is f of x. And the idea is that you want this f of x value, or this distance, to be transferred somewhere along this x line. And how you do that is actually through the identity map, which is you map it to here and then all the way down, because you want this y value to be an x value on the x-axis. So you would actually map this to some point here, and then the identity map would bring it down. But this is not a real transformation, because this identity map is not in the function. It's just kind of there to show you, or to be an intermediate in transferring this fx value onto this line. So this is also fx. This is the same value. And then now you want to apply the function value to this one. And now this happens just to be down here. And then again, you go left. In this case, went right, but this case you just go left. I don't know. Maybe there's a rule for how you do this, but basically fx, it maps fx to this, which is f2x, not the second derivative, as the book says. The book says that if there's no parentheses around here, it's just applying f twice, which you need some notation for that. And this, you see like this line is just there to like kind of show you which point is pointing toward what, But this is actually where the map happens, and this is also the second time the map happens. So you keep drawing this, like these lines or these arrows to this identity map, and you see like it kind of converges a little bit, as you see right now. And you map this back to x, or this is would be f2 of x, and then you map this back to f3 of x, f3x, and then you kind of keep going, keep going, and then it kind of spirals down. And I think this is kind of interesting because this is basically what a fractal is, or it kind of represents a fractal. I'm not exactly sure what like formalized intuition a fractal is, but like kind of, you see this kind of keeps going down, and if you zoom in, it kind of repeats itself, which is kind of cool. But the idea is that if you have a fixed point, or a periodic point, this box is gonna look like it's gonna look like closed, if that kind of makes sense. So it would just look like this, and it would just keep mapping to itself in a closed loop, and then periodically. But if something's not a periodic point, it'll kind of just like keep bouncing around, or sometimes it'll like diverge off to infinity, and sometimes it'll converge to something. But the idea is like, for example, this x is not a periodic point, as you can see geometrically, instead of just algebraically determining it, because this phase portrait shows that it doesn't converge, or it doesn't like have like a set path. So just something weird happens. And the book also talks about something called hyperbolic points, where the derivative of the nth iteration on a point is not equal to 1, then it's called hyperbolic. And that's for a particular function and for a particular point. And some points might not have any, might have all periodic points, or like none. And an interesting property is that if the derivative is less than 1, I mean, there's another case where it's greater than 1, they call it an attracting periodic point, or a sink. And the idea is that every point in a neighborhood of that, it exists an epsilon neighborhood, then all points, if you keep mapping f to some point in around a neighborhood, it will eventually get mapped to p, which is actually kind of interesting, because it also makes sense because it's called a sink, and the sink kind of funnels things toward the center. And it's interesting because it doesn't matter what the neighborhood is. No matter how far a point can be from P, it will still get eventually mapped back to P in some finite amount of n iterations. Okay, now it talks about the hyperbolic fixed points when the derivative is greater than 1. And that basically says that the complete opposite, which is any number in any interval, will eventually get sent outside of the interval. So it doesn't matter how far away or how close to the point is to P, at some point, if you keep adding f or applying f, it will get arbitrarily far away, which it's exactly opposite, because I guess they call it a repelling fixed point. It's kind of like something repelling something away, like a magnet or something. And they call it a source, which is not as intuitive as a sink, but I guess a source means like it emits stuff, so like things go away from it. And it relates it to an unstable set, I guess, because things they move around a lot, so I guess that means what unstable is. And then it starts with bifurcations, which is it's kind of like when something like weird happens as properties of fixed points, or hyperbolic fixed points, or periodic points. And the idea is that like when a parameter is being changed, things will happen when it reaches a certain point. And it's like a good example of x squared plus c. Okay, so this is basically the function that's described and c is the parameter. So you can change, where this function goes. And you see that when c is 1/4, exactly 1/4, I mean, algebraically you can obviously calculate this, but geometrically you can see that it touches at one point. And at one point, this actually becomes a fixed point because it collides with fx equals x. So something happens though. And when c is greater than 1/4, then there's no pure, fixed points. And what happens is when you barely get outside, the roots kind of like double, right? There's 2 points now that intersect with y equals x. So, and when you go down, these 2 points just get farther and farther apart. So something is happening here, as the book says. And I guess there's a lot more examples of this in different names for how it works. Yeah, and so basically, there's this other example where that's unrelated to this, but you basically use the implicit function theorem to basically say that like you can determine the roots, how the roots behave for the function based on what this is. So it even works for like a quintic, even though there's no generic formula, or I'm pretty sure any other polynomial with finite degree. And essentially, like if you move a around, these 2 roots in the middle don't change that much, but this root changes on the left pretty drastically. And so there's something to be like, said about that. And there's bad points when the derivative is like exactly equal to 0, because you see that there's no roots right now, and then now there's 3 roots. There's actually 1 here, but at c equals 0, something happens because the root will split into 2, or 0 becomes to 2 as c becomes negative, and as c is positive, there's only 1 root on the left, and vanishes. But I guess this is also bifurcation because that's why by the implicit function theorem, it says that this derivative cannot be 0, because if it is 0, then something bad could happen at this point, and you want to exclude stuff like that. So I guess like the implicit function theorem kind of hides this bifurcation in it, which is kind of cool.